Hello folks, today we'll talk about linear independence, continue talking about linear independence with some more examples and properties, material from 1.7. So let me just recall our kind of basic fact from last time. A collection of vectors, let's say A1 through AN, is linearly independent, right, if and only if the vector equation x1a1 plus xn equals 0, right? So this is a vector equation, has only a trivial solution, right? So if we're setting this equal to 0, we know that there's a trivial way to solve this thing by putting all the weights to be 0. By definition, if that's the only solution, we say it's a linearly independent set. And then the key idea is that if and only if the matrix, I'll call it A, that I get by just putting these as columns, the usual thing, this thing has a free variable. Or another way to say that is missing a pivot in some column. Okay, so that's going to be our main kind of observation that we're going to basically apply to different cases today, different situations. So what we want to first do is, I first want to look at small collections. So what about if you had just one vector in the collection? So if you just had one vector, say, v. Well, notice that, if you got one vector and you make the matrix that, consists of just that one column, then that thing will have a pivot if and only if there's some non-zero entry in the vector. So this is linearly independent. A collection of one thing is linearly independent if and only if v is not the zero vector. Okay? So as long as your vector is not the zero vector, that collection consisting of just one vector is going to be a linearly independent set. So just to get that out of the way, what about two vectors? Now we have, say, v and w. So I think I'll do this with maybe an example. So for example, if you took 3, 1, and 6, 2, and let me compare that with 3, 2, and 6, 2. So notice, how are these different? Well, in this case, the second vector is a scalar multiple of this one, and in this case, they're not, right? So if I had to draw a picture here, right, I had kind of sketch out the pictures. So 3, 1 is like 1, 2, 3, 1. And then 6, 2 is 4, 5, 6, 2. So it's like this, right? 3, 1, and 6, 2. And here we had 3, 2, and 6, 2, right? So this is parallel, this is not. Now notice what happens when we do the parallel collection. So I'm going to do the usual thing now. I want to consider the matrix A is 3, 1, 6, 2. So that's the matrix I get for the first collection of two vectors. This reduces to 3, 6, 0, 0, right? Because this second row is just minus 3 times, well, it's 3 times the first row. So when I clear below the pivot, I get this. And so this is missing a pivot in the second column. There's only one pivot in the first column. And so this is a linearly dependent set. And the fact here that, well, maybe I'll just write down and we can discuss it more in our meeting, is that a collection of two vectors, so let's say v1 and v2, this is a collection of non-zero vectors is linearly independent if and only if one is not a multiple of the other. Right. So that's an if and only if condition. Actually goes both ways. So just note that if you had C1 V1 plus C2 V2 equals 0, for some non-trivial solution, so let's say C1 is not 0, then what you can do is, right, just collect your things here. So you can say C1 V1 equals minus C2 V2, and then you can divide by C1 to say that V1 is actually equal to minus C2 over C1 V2. So what you're saying is that if this is a dependent set, if you have a linear dependence among the vectors, in other words, a non-trivial solution to this vector equation, then what you get is, in fact, V1 will be a multiple of V2. So dependence actually implies that. Okay, and okay, so that's the case with two vectors. It's very nice. Let me just emphasize that when you have three or more vectors, there's no nice tricks here that, so we have these kind of nice tricks for the case of one vector and the case of two vectors. But if you're three or more vectors, then this will require row operations in general. Okay? But, okay, so that's the case of kind of small collections of vectors. Let me also write down an important fact here that, so here's another fact or theorem, is that a set, let's say S is V1 through Vn, this is linearly dependent. So dependent if and only if at least one vector in the collection can be written as a linear combination of the others. Okay, so I'll show you this in a second. But let me also emphasize just while we're here is that I'm not saying that every vector can be written as a linear combination of the other. I'm saying at least one. Okay, so there should be at least, so if you have a collection of 100 vectors and you know it's a dependent system, then maybe the 97th vector can be written as a linear combination of the others. So maybe I'll save the example for our discussions because I want to give you guys a couple other facts. Another important fact is the following that says, basically another trick at how we can identify dependency in a collection of vectors. So here it is. Suppose S is a set of, let's say, n vectors in Rm. Okay, so it means that S is V1, V2, Vn, and each one of these has m entries. Okay, well then if n is bigger than m, then the collection S must be linearly dependent. Okay. And what's the proof of this? Well, here's the proof. So the proof is that, let's look at the matrix. So let's consider the matrix as usual. Let me call it A. So I'll take V1, V2 as the second column. These vectors, as usual, will be the columns of the matrix. And what do we have? So A is it's an m by n matrix, right, the way I did this. So because there's m entries in each vector and there's n columns. And we know now that n is bigger than m, and we've seen this before, right? So if you have more columns than rows, then this means that we have at most m pivots, because you can have at most one pivot in every row, and this implies that some column, at least one column, is missing a pivot. And we've seen this before. This is how we started off this lecture. This implies that the collection V1 through Vn is linearly dependent. Okay, so this is another example of like the shape of the collection, right? So if you have more vectors than the size of each vector, then you know it's a dependent set. And that's a very nice trick because you don't have to check anything. There's no row reduction necessary. It's an immediate observation. Let me just note, so caution or note, if n is let's say less than or equal to m, then no information. Okay, so you can't make a similar. Okay, can't make a similar observation if you have the number of columns less than or equal to the number of rows. Okay, and then I think the last trick I want to just give you guys before we sign off, last kind of fact here, is that if a collection, let's say v1 through vn, contains the 0 vector, then the collection then S is also linearly dependent. And okay, that's a useful fact, just a pretty immediate reason for that. So here's the proof is that, well, let's again consider A, the matrix I get by putting those as columns. Well, we know one of these vectors is the 0 vector. So since, well, so this looks like, it's something, something, something. At some point, I've got all zeros here, right? And now when I go to row reduce this thing, well, I don't actually care what's going to happen. I know that in this column, I'll never introduce anything non-zero. So this will be missing a pivot in some column. And again, that proves it, because once we are missing a pivot in some column, it means we have a free variable in the matrix. And maybe just to finish this off, this implies that A times x equals 0 has a non-trivial solution, which implies that the collection v1 through vn is linearly dependent. Okay, so the usual story. Okay, so I think I lost focus there. Hopefully we're back. So I mean, those are, again, some kind of tips and tricks regarding linear dependence and independence. And we'll discuss some more examples when we meet in class. So we'll see you next time.